Hello and welcome to Haman Nature. I am Adam Haman, and with me is a buddy of mine, Bernie Jackson. Bernie is an electrical engineer that I know. I met him in Tom Woods' School of Life, which is the impetus for this here podcast creation, like it or not. Bernie is an all-around smart fellow, very mathematically inclined, and we're talking today about a talk he's given in several occasions that I got a chance to see a video recording of, which is fascinating. He titled it "Forbidden Numbers Ate My Brain." And I want to just read a few things from an intro that I found somewhere on your website, Bernie. Here's something you said. Numbers are logical and orderly. We, quote, turn the crank and they follow the rules. But you say that math isn't about turning the crank any more than reading is about sounding it out, or that art is about memorizing that blue plus yellow equals green. You say, like art, math is inherently creative and driven by intuition, and it can be subversive and has led to controversies and dangerous ideas. Math is about shifting your perspective on purpose to solve a particular problem. It is inherently creative, not mechanical. And then you finish with, the only rule is that the rules will change. Cool. Sounds like Fizbin from Star Trek, or Calvin Ball from Calvin and Hobbes. So this all sounds fabulous. This is going to be great. Welcome to Haman Nature, Bernie.
Thank you, Adam. It's good to be here. The talk you mentioned was for high school students, and I was really, I really wanted to impress upon them to stop seeing math as a rote a mechanical enterprise, because we go through school and people tend to put math and science to some extent off to the side in a different category than the other disciplines, than things like English and art and stuff like that. And there's a real feeling that, like, you've got the formula guys over here, and then you've got the, creative designer guys over here, and that they're fundamentally different things.
Yeah. And, that's a category error for sure.
Mm-hmm. Yeah, it's a real pet peeve of mine. And so I wanted to tell these high schoolers who this was a thing for math. It was a national mathlete organization called Mu Alpha Theta. So these were, people tending to go into calculus and stuff. And so I just wanted to give them this other way of looking at their field and not put themselves in a box like this.
No, you did a great job. Let's start with some of the history of numbers and math and whatnot, and the various paradigm shifts that you're talking about. And why don't we start with why we should be interested in what's his name, Hippasus of ancient Greece? What happened? What happened with that fella?
Yeah, well, he was maybe killed for math. If not killed, then definitely banished. There's three possibilities in history, and they don't know which one for sure is the real one. But he was exiled from whatever area of Greece, and or thrown overboard. They took him out to sea and threw him overboard. Or the other story is they were all out to sea, and the gods were so angry at him for math that they sank the ship. I'm not really sure exactly which one happened, but it was definitely about math, and it was about the square root of 2, no less. That this dude got in that much trouble over the square root of 2. And so I picked examples like this because I thought they really illustrated in one punch how math is not this discipline of certainty. Okay, and you have to understand what I mean by that. When I say 2 + 2 is 4, of course I'm certain. I mean, given the definitions of 2, we're completely in theory world when we say that. We're not pointing at real things. But 2 is a concept, and all the other concepts, 2 + 2 is 4. That is certain. So no one's throwing that away. But we're just saying that math keeps bringing us into things we didn't. Math keeps bringing us to ideas we didn't expect. that don't conform to what we thought was there. And then what we do about that, that's where the controversies are. And you wouldn't think these things are hidden in math. You just start. I mean, it all comes from counting. All we were ever trying to do was count how many sheep were in the pen in the backyard, so we could, trade them with people. That's honestly why. That's all we ever wanted to do, right? And just to do that, we keep getting into, like, irrational numbers came up real fast. That's what Hippasus was in trouble for. And anyone who went through school, high school, probably had a brush with imaginary numbers, which is just the dumbest thing, right? If you don't get why we should be talking about that. And they even called them imaginary numbers. Like, really?
Well, before we go all meta and get into the present, I want to stick with these fascinating Greeks.
Yeah.
Can you tell us more about the way they thought about numbers, with the ratios, and why something as simple as bisecting a square room or drawing a diagonal across it suddenly just blew their minds and made them question their own understanding of reality so much? It seems like such a simple thing.
Absolutely. Good host chops there, Adam, pulling us back to the thread. So you go from the simplest possible counting and drawing squares, and we all know the Greeks. We know the Greeks as geometers. This happened around the time of Pythagoras. Pythagoras is the one who gives us the theory about the triangles. And so imagine you're Pythagoras and you're doing squares, and you draw that diagonal down the square. And what happens is you ask yourself, of course, you can measure one, like you can build a room and you can measure it, but you're not getting like the mathematical answer when you measure it. You're getting it to the nearest eighth of an inch, or whatever method you're using. That's the empirical result, which isn't perfect. But what's the perfect answer to the length of that diagonal in a square? And what happens is you end up having to find something that you can multiply by itself and get the number 2. And of course, it depends. It depends on the size of the room and the units. It might not be exactly the number 2 we're talking about, but there's some, whatever length the sides are, the diagonal, you have to be able to square the diagonal and get double the length of one of the sides. That's what's really matters here. So it's the ratios that are coming about. And to us, that sounds like, just take your calculator, and do it. Like, what's the problem? The calculator is going to give you the series of numbers, and we've all been told that the square root of 2 is this annoying thing called an irrational number, and the numbers are going to go on, and you'll just truncate at the end. But the Greeks didn't do that. The Greeks, not only did they not have calculators, they didn't have the decimal point, and they didn't have, they did count in base 10, but they didn't have zeros or the decimal point. Believe it or not, they wrote their numbers as letters. They just took the first 9 letters and used them as 9 digits. And they didn't have a 0 at all, because they didn't think of 0 as a number. Because 0 is when you don't have anything. So you don't count if you don't have anything. So there's no 0 in their system. And
it always, one of the things about your talk that made my hair stand on end is that we learned the Pythagorean theorem is a squared plus b squared equals c squared, but that's algebra, and the Greeks didn't have that. So how would Pythagoras have thought of his own theorem? Because it's geometrical, it's not algebraic.
Exactly. Yeah. Well, they had the idea of squaring, but look at the word square. Like, when you hear square, you probably imagine a little 2 up high. But that visual wasn't there for them. A square means that, right? That's what the word is. So you said square, and they thought.
For our audio listeners, Bernie just did the Uma Thurman thing from Pulp Fiction. Square, baby.
Yeah, sorry, I forgot about the audio thing. Right. So an ancient Greek, here's the word square and pictures an actual square. And so when Pythagoras says the square of a length, he literally means make a square with that size of a length in both ways, and then look at the area inside the square. So this is visual geometric thinking, that the quantity called a square is a box. It's the filling inside a box. So they said it like a word problem. The sum of the squares of the legs of a right triangle is equal to the square of its hypotenuse.
I love that visual. That's what it means.
That's it. That's the
Yeah.
words. That's what they said. They said the words. And if in like, there's an iconic math drawing of a right triangle with squares sprouting off of each side, each of the three sides. Mm-hmm. That's visualizing the way a Greek would have thought about that, with not any kind of an equation, just those three boxes arranged around the sides of a right triangle. That's the picture they had to relate the squares of legs of a right triangle to the square of the hypotenuse. And so they didn't have a cheat sheet with the little equation written. They literally just had those words. And they would, and even our old school, like a schoolhouse, from 1880 or something, the little kids are sitting around and they're all repeating what the teacher says. That's the kind of thing they were doing because everything was words.
So, as you also say, they didn't have the concept of the number line, but they did have things that would have been inside our number line, but they thought of them in ratios. In fact, they thought of everything as ratios. And
yes.
So, yeah, using that as a building block, tell us again the story of Pythagoras and Hippasus and the heresy that was such a big problem.
Right. Well, Pythagoras was kind of a rock star. He was, since we hear about him in our geometry book, you probably think of him as like a, Poindexter, white collar, shirt buttoned up, geek type of guy. He was kind of a rock star cult leader. And but in the context of numbers, of course. And for ancient civilization like that, as mentioned, of course, they started numbers by counting, and then you quickly come to subdividing things. And as soon as you subdivide stuff, like you say, hey, the three of us, let's go into this partnership and we're going to sail our ships around and trade with people, okay, I'll get a third, you get a third, you get a third. Now you're doing fractions because you're splitting things in thirds, or then maybe you've got five, or let's say you've got four partners and one of them is going to have twice the share of everyone else. So now you've got like 2/5 versus 1/5. So there's 5 parts, but one guy's going to get 2 parts and everyone else is going to get 1 part. So in that world, talking about fractions is pretty natural. It's the next thing past counting. And that was their world. And we call those rational numbers. And they called them ratios. I don't know that they would have used the word fraction, but to them, it was all about ratios. And we can still see that in our linguistic heritage because we say rational to mean sensible. And rational is just a word for ratio rational means it's based on ratios. So if you're dealing with a ratio, you're dealing with a quantity, like a mathy, sciencey, objective thing because it's a ratio. So their entire worldview is that all the objective things around that you could measure, they all amounted to some kind of ratio. And a ratio is a number, and a number is a ratio. And they had noticed things like Pythagoras was known for playing with tuning forks and strings. So he had a string like a looped string. If you divide it perfectly in half, then you have an interval called an octave, where you pluck one side of it and you get a note. You pluck the whole thing and you get a note that's an octave lower. Whereas if you don't have a good ratio between the string lengths, you get dissonance and horrible sound. Yeah. If you have a nice ratio, all the pleasing sounds are like a ratio of 1/2 or 3:2 or 4:3, all the major scale ratios in there. And they had lutes and they did music and they tuned all their strings to those ratios. So they were very attuned, so to speak, to how ratios drove everything. And they looked up in the sky and they thought that the way the planets, you've heard the term music of the spheres, because the spheres, the planets seemed to move with a certain ratio, and they didn't do orbits because they didn't have the whole heliocentric thing, but so I don't know exactly what ratios they were looking at, but they definitely were seeing metrics up there that had ratios, and they imagined them making music, and this was all tied together with their view of the heavens. So they had a very ratio-driven metaphysics.
And in fact, if it's not a ratio, it's not real. So from their perspective, you illustrated in the talk is viewing things like pi segments. So back to the square root of 2 thing, they assumed that if you could just figure out a way to slice the pie into, infinitesimal small, eventually someone's going to figure out, they thought back then, the way to divide the pie so that you multiply these, but it just never worked out, right?
Right. And I bet you, like, right now, anyone listening to this, I can still find the same intuition. I'll bet that you intuitively think that if you slice the pie into like a billion pieces, surely if you just take the exact right number, you could hit anything perfect. You could hit pi, or the square root of 2 or some number. You could hit that ratio perfectly by cleverly choosing maybe not a billion pieces, maybe 1,000,000,001. How about that? There may be 1,000,000,003, right? There's so many, and you could go to quadrillions upon quadrillions. If you chop that pie up so finely, surely you could just pick the right number that hits this length, like the diagonal across the square, or any of these transcendental numbers that we've studied, like pi or e or whatever. The idea that there is no such pie slice configuration that can ever hit that number, that is a crazy idea.
And yet,
if you can't admit to yourself right now, even though you took math, if you can't admit to yourself that that is a crazy idea, then I invite you to just meditate a little bit, because that's what they were like us, except they never had a teacher tell them that. And they were grappling with that in the void, with nothing to compare it to or nothing to bootstrap that on. And so you're told, like, you've got this worldview that numbers are ratios and they drive nature. And then you just draw a square or you build a square room and you're looking at this thing, this diagonal thing that is not a number, but it's right there. It's physical.
So it's back to the murder mystery, the original deep state rock star Pythagoras, he figures this out first, right? But he keeps it a secret.
Yeah, and he figured this out. He almost kind of invented algebra. I can't quite reconstruct the proof right now, but I was reading through it, a few years ago when I was working on this talk, and basically he was saying things like imagine the number, look at the ratio, like what's the top number and what's the bottom number, and if you would need an even number of 2s and 3s or whatever in order to take the square root. What he's really saying, I guess, what he really found is that there are numbers that you can't. There are things you can't make by squaring. Is that fair to say? I think that's what we're saying. Yeah. So like you can't make the number 200 by squaring, because you can put the 10s in there. You can have a 10 and another 10 to make the 100 part, but you can never make the 2, because you'd have to have more, because 2 is prime. So you would have to have a couple of things to multiply together to make the 2, but 2 is prime, so there aren't any such things. That's basically the logic that he went through.
So Pythagoras, genius that he is, figures out that everything the Greeks think about math and reality, in essence, isn't true.
Right.
So,
small problem. I mean, it's almost like in the early, it's almost like in the Middle Ages, if some monk had just proven that God didn't exist within a Catholic church.
Right.
That's your whole job. You're in the Catholic Church and you're a monk and you're trying to be a good monk, and you just stumble on this proof that there is no God. Like, what are you supposed to do with that, right? This is what it's like. So Pythagoras stumbles on a proof that that there are numbers that are not squares of anything, or that there are things, yeah, that's the same thing. There are things you just cannot take the square root of.
So their entire worldview is belied by something as basic as a square room with a diagonal cut
Yeah,
across.
right. You can, because you don't even have to do anything fancy to get it.
So rather
Just
than admit that God isn't real, he shuts up until Casasis comes along.
yeah. And so he's got this inner circle because he's a cult leader. So he's got this inner circle and they know, but they're not telling anyone else because they don't want to, it's kind of like when the aliens land and the government won't tell anyone because like they don't want everyone to panic, So
It's just like that.
Yeah, so they won't tell anyone about irrational numbers because they don't want everyone to panic. And they're having their little emergency meetings and they're trying to like figure something out and maybe I don't know. What could they be figuring it out? I don't know, but they were panicking. And so ultimately this other guy, and I think I read and we don't know everything about this, but there's an idea that Hippasus may have actually discovered it himself in parallel, because Pythagoras was not the only one to see this. He was just, the only one in a position to really care. So Hippasus either independently discovered it or was in the inner circle. He was kind of the Judas of the inner circle. He was definitely in the cult. And so he becomes privy to this knowledge and he's not supposed to tell anyone, but he does. Because, how long can you really keep that a secret? Right? So yeah, sooner or later, someone was going to tell, and it was poor Hippasus who did. And so they killed him or whatever, or exiled him. His tomb exists, so they exiled him and built his tomb, or killed him and put him in it, or whatever.
So either way, massive paradigm shift. And there are others. Do you want to talk a little bit about how we came to have a zero?
Yeah. The zero's hilarious. There's a book called Zero this was, I think, the first thing I came across that got me thinking down these paths was I read this book called Zero in 1999. I think I was relatively new at that point. And I was really floored by the idea that there wasn't a zero for a long time. And what would life be like if you didn't have zero as a number? And so, first of all, there's like a small version of that and a big version. The small version is just that you don't have the digit to write. So like you're counting to 10, you write 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you have to write the word 10 because you don't have a number for it. And then you can write 11, 12, 13, 14, blah, blah, blah. That's like just like a small technical, annoyance. But the bigger concept is you're not allowed to make zero into a number because there's a very perverse idea about making something that refers to nothing, or even allowing the lack of something to be a quantity. It's a kind of messed up concept because like if I can say, if zero is a real number on equal footing with all the other numbers, then I can say, I have sheep. I have blank sheep. Fill in the number. 1 sheep, 2 sheep, 3 sheep, 0 sheep. Zero's not the same as all those other ones. Like I'm someone who has never owned any sheep. Like I'm not even a farmer. I don't live on a farm. There's nowhere I could even put a sheep. It's not the same for me to say, I have sheep, asterisk 0, haha, as opposed to someone who like actually has 10 sheep and they're going to put 10 in that blank. Like those really are different categories, as opposed to a guy with 9 sheep and a guy with 10 sheep. And the only difference between them is the number of sheep they have. But I come along and try to be like one of them. I'm just like one of you. I have 0 sheep. No, I'm not like them at all. See, so there's a little bit of a lie in there, and you're embracing this lie in order to promote 0 to be a number. And of course, we're just so past this being a problem because we live in this world has 0.
So we were being held back artificially by these math theologians, these philosophers, and we were freed from this constraint by who else? Commerce and the abacus.
Exactly. Yeah, and I love this part, being a libertarian. I love how the first, right, the intellectuals are all wrapped around the axle about 0. And the commerce people are going, look, man, I got 100 clams. I added them up on my abacus. 1 minute I had 99. and you're happy to write a 9, and of course we're writing the letter I for 9, but we're going to write that letter and then the next letter. You give me one more clam, I have 100, and now I can't eat. I don't have a number. They're like, this is not the way of the future, guys. We're not going to do it this way. So they're like, we just need a thing that you put in the empty spot. When the abacus comes up empty, we're just going to make this thing. We're going to make like an empty. How about an empty circle? What about that? Empty circle, right? So we write a 1 and an empty circle and another empty circle, and this is just showing that here's what your abacus would look like if you have this many clams.
In your talk, you go through a period where they literally would write, if it was 1,001 clams, they'd write 1 and then some sort of a space, or how do you write 2 spaces and then another 1? And that gets a little confusing. What do you mean I owe you 1,001 clams? It looks like 101 to me.
Mm-hmm. Right, that varied. There were, I think, like places like the Babylonians were writing that. They called it the cipher, the 0 placeholder. They were writing that, and then other cultures were like, those filthy people with their here. We would never be like them, and so then they would write an empty space because they wouldn't deign to write the cipher. But as you said, how do you count how many empty spaces there are? And if you're, a smooth, shyster commerce guy, you're like, well, I don't know if there's 2 zeros. I'm thinking it might only be 1 0 there. So I don't owe you 1,000. I only owe you 101, not 1,001. It says right there on paper, right? So you could see how that wasn't going to last long. But they needed the 0 more than anyone else. So they just started doing it. And then, everyone else conformed. I also love how when that little anecdote about the Italian bankers being forced by law to do keep their books in Roman numerals.
That's wild. That's just wild.
Numerals. Imagine how it's in your checkbook in Roman numerals.
So that's another huge paradigm shift. But there are plenty others. Do you want to just walk through like a few of your favorites, or some of the ones you think are most illustrative of your broader point that math ain't turning the crank? It's about being creative and conjuring up a new way to see things to solve problems.
Yeah. I like imaginary numbers because, one, I'm an electrical engineer, and we couldn't live without imaginary numbers.
Sure.
Also because I think for most people, like if you've been to high school at all, you were forced to gargle imaginary numbers a little bit and hated it and ran away screaming. And so I think that gives you more of a flavor of what the Greeks were dealing with irrational numbers.
Right.
Because like irrational numbers don't bother us at this point because we've all seen
both of those names are like designed to be scary.
Right. Yeah. Right. Irrational, we just kind of look past that. But we've all seen the square root of 2 on a calculator and we don't have a problem with it. But I think we all have a problem with imaginary numbers. So if you want to sympathize with the Greeks, just think of your relationship with imaginary numbers and realize that that's how they saw the diagonal of a square root. It's this imaginary number was forced on them, and they're not even sure what it is, and they're still not sure if they believe in it, but it's right there, and they can't do their theory without it. And so the only reason, imaginary numbers, again, no one wanted irrational numbers. No one wanted imaginary numbers. All we were trying to do was count. But the instant you do algebra, nothing stops you from writing x squared plus 1 equals 0. That is the simplest polynomial you could ever write. And the answer is the square root of -1. So like you have a choice. You can say, this is an illegal equation that you must never write. And then you're like the people holding back 0. Or you can say, fine, what kind of number would have to exist for this to have an answer? And the answer is, but what's interesting about this is you only have to take one concept. If you just allow -1 to have a square root, then that whole world opens up and you can do all the polynomials and you can do all the roots and all the weird things. It's just one little door you have to open. So that's interesting. Even if you don't believe in that, like it's really interesting that one little spot, it's like there's this one hole in the dike, and if you just plug that hole, there's a whole new world that opens up. And then it turns out it actually has applications because, as I said, electrical engineering. But the ability to say that because otherwise you have to say there's this huge category of algebraic expressions that have no answer. But once you allow that square root of -1 to exist, then those things have an answer. And even though that answer, it's non-physical, you can't make something that's the square root of -1 feet long. But if you carry that answer through additional equations to get to the end of something, that's basically what we do, electrical engineers, because in the real world, there are no imaginary numbers. But we carry imaginary numbers through the equations to get to the end, and we can get somewhere we couldn't have gotten before.
It's fascinating, and I hope we have time to hit this concept again and again, because we know that this thing we don't understand has application in the real world, which reminds me of, how calculus was invented with this weird thing called an infinitesimal that may or may not exist, that defies all reason. We can use it to figure out things that are true, but it's based on a thing that we can't comprehend. That's fundamentally weird and true, and I don't know what to make of it.
Yeah. Part of that is, you can get calculus without thinking about that. Some of this is that it's the piece, whether an imaginary number or an infinitesimal. The thing about it that's not real is that it's just a step along the way of a real chain of thought. So it's kind of like, it's not a place you land on. So the thing that's dodgy about it is that you're focusing on that spot. I wish I had a good analogy for this.
Maybe it's a technique and not a thing.
Yeah, it's not.
Or better thought of. Yeah.
Mm-hmm. It's like you're artificially extracting a part of the thing and trying to look at it as its own thing, but it's just a part of a thought process. If you put it out by itself,
let's try and motivate what's going on. Again, you originally designed this talk for kids, and I love the story of Gauss's sum, because it's perfectly aimed at kids. We're sitting there in their desks, and you get one over on the teacher. Why don't you tell that story, and as you do, maybe try and overlay it onto this thing where what you're doing is a creative technique, not like finding a new particle in the universe or something.
Right. Yeah. Gauss's sum is adding up the numbers from 1 to 100. And I like this story because it's probably the simplest, most concrete illustration of what I'm saying about math being a shift of perspective. And I claim that not only the big ideas of math, like we just talked about, some big ideas of entire new types of numbers that come up, but even the little ideas when you're just adding numbers, even that, you often shift your perspective in order to make the problem, either to make the problem easier or to make the problem even doable at all. You have to look at it the right way. And so this story about Gauss is that, he's the famous mathematician that we named the Gaussian bell curve after. And when he was a little boy, supposedly, I don't know how, this could be one of those stories that didn't actually happen.
Sure.
This is one of those
story anyway.
He was a little boy in elementary school, and either he was cutting up in class and the teacher wanted to shut him up, or the teacher just gave the whole class this crazy problem to keep him busy. But the problem was, add up the numbers from 1 to 100 and tell me what the answer is. So at first glance, you have 99 math problems that you need to do. And the first handful are easy because it's 1 plus 2. But then it gets tedious and annoying, and you're going to carry the 1 and the 2. And, so what are the chances any of them are going to get through and get the right answer, right? And if they told you the answer, how would you even know if it was right? So, but Gauss just looks at that. And what I would call the shift of perspective is, instead of looking at this as 99 disjoint math problems, I'm going to notice that if you line them up, imagine all those numbers listed out in a row. The first one and the last one add up to 101. And if you move in to the second one and the second to the last one, you have a 2 and a 99. They also add up to 101. And then you have another pair. So you actually have 50 pairs of 101. Boom, that's the perspective shift. So if you see that, you see it. And if you don't, you don't. And let me ask you, where did you learn in this allegedly formulaic discipline called math? What's the rule you invoked to see that? You tell me, where in the rule book, which law of algebra or geometry did you slap down on the table to get the right to see it that way?
Yeah, which crank did you turn? There was no crank. You saw things differently.
Yeah, you intuitively, creatively saw it that way because you just noticed. Something in you just noticed. And as soon as you see that, then you get the answer in 5 seconds. It's like, well, it's just 101 50 times. And if you're a 9-year-old, maybe you don't know how to multiply that, but you can probably add 101 to itself 5 times. And then you're like, oh, well, I just have 10 of those, so stick a 0 on the end. Or there's a lot of ways to get to that when you don't even know multiplication necessarily. But yeah, so Gauss comes back like in a couple minutes and he's like, the answer is 5,050, teacher. And the teacher's like, what are you, smart ass? The teacher probably didn't even know what the answer was, right? So then the joke's on you, like, go in and check my answer.
Right.
Right. And yeah, so I love that story. But that's I can frame pretty much any, like even just adding 2 3-digit numbers together. I illustrated in my talk how even that, if you don't just follow the formulaic way of adding down the columns, if you just look at like, if one number happens to be close to 100, you can kind of like move bits from the other number over to that number to make it 100. Like if you're creatively figuring out what they add up to, there are all kinds of small perspective shifts, even in calculation itself.
If I'm not mistaken, I think part of that new math we heard about was them trying to change the crank that you turn from what we learned as kids to something more like what you're talking about.
That's what it sounds like. Yeah, that's what it sounds like. But you can't make a formula out of it.
No, it's weird. It's interesting. Yeah, trying to make a crank where that's not what you're doing.
Yeah.
So do you have any other massive perspective shifts to illustrate your cause?
Yeah, let me just say there's nothing wrong with turning the crank. Like you
Sure.
You want to get to where you understand something enough that it's systematized and it's boring, and you can just, no matter what numbers you give me, I can add them together. And I don't have to be creative to add them together, because that's how we get adding machines. The adding machines are not creative. The only thing they can do is follow the mechanistic process. So if you want to mechanize that, you've got to get to turning the crank. And when you reach turning the crank, it's because you thoroughly understand the problem. And before you thoroughly understand it, and you're just, flying by the seat of your pants, you're lacking something. And it's good to get to where you've figured that out. So I'm not anti-turning the crank at all. I'm just saying it's not what math is about. It's just a tool. It's like learning blue and yellow is green. That's not art. You need to know that to do art. But that's not all art is.
Yeah, not even close. I'm just fascinated by what these shifts did for us as a civilization and how threatened the previous members of the cult were by having the rug pulled out from underneath them. It's a thing that could get you killed, could get you cast out. I'm just fascinated by what an incredibly dangerous thing it is to relabel the way we look at reality. That's fascinating.
Absolutely. Yeah. And so in the talk, one of the shifts I do is I say, well, now that we've talked about perspective shifts, let's shift our perspective on how we view a perspective shift. Because that's a very mathy thing to do, is to turn something on itself, right? So you've got this idea of perspective shift, and let's ask, how else could we see the process of shifting perspective? We could look at it as relabeling reality. Because if I'm looking at reality a certain way, I've labeled it a certain way. If I look at it a different way, the categories shift, and I'm going to relabel the same reality a different way. That's
Yeah,
really
that
cool.
goes deep too. A concept I talk about a lot on the show is that when you change your perspective, your framework, you literally change not only the way you think, but the way you see and hear. Your frame
Absolutely.
affects your even your perception,
Hmm.
which is amazing.
And you change the truths you're able to see,
Yep.
because this is an extension of, like, before you accept irrational numbers, there's certain math you can't do. Before you accept imaginary numbers, there are certain math you just can't do. There are things you cannot solve. You have to look at it from the perspective that imaginary numbers could be a thing, and then you can get you can get to places you couldn't get before. And so the analogy there is, well, if I let myself relabel what I'm looking at in a fundamentally different way, and it's important that I still have to preserve the truth of what I'm seeing. I can't just relabel nonsense. But if I'm looking at it from really a different angle, metaphorically, and I label it a completely different way, then those labels let me see connections I didn't see the other way. But the problem is, now you're fighting with the people who are still looking at it the first way. And they're convinced that what you're saying is false,
Right.
because it doesn't come about from there. See, what they're doing, they're looking at stuff, they've labeled it, and they're carefully, logically proceeding through from the way they labeled it. And they come up with certain things and not with other things. And now you're getting to places they're not getting to. And so you must be false. So until they come around to how you're looking at it and label it your way and see where that goes, and until they see
And
from
see
the
the
start,
usefulness of it. I mean,
yeah,
again,
right,
it can't be just nonsense. There has to be you have to have gained something in the
yeah,
relabeling and be able to demonstrate that.
right. You've not only gained something, but it also, there's something about the labeling that makes conceptual sense. So they'll accept it. And this is our problem in quantum mechanics.
Yeah.
We've got a mathematical system that works. It really works, but no one has yet really made sense of how things are labeled. I mean, you have to treat probability as if it's a physical quantity.
There's an infinite number of universes that pop into existence every half a second, Bernie. What's so hard to understand about
Give me a seriously, like, I mean, every continuously vary, like, I mean, I just wiggled my finger. So every possible different way I could have wiggled my finger is a different universe. Never mind all the other stuff that just.
Don't act like it's crazy. It's 56. You just created 56 universes. Out of what
Well,
matter? Don't ask follow-up questions.
56 quadrillion. Like, how many ways could, look at all the places there are that my finger could have stopped. And so even if you believe it, that they're all quantized, where you're just assuming that.
I mean, if you just want an F, Bernie, you could get an A. It's so simple, but no, you got to be difficult.
Yeah. Again, like, fine. If something like that is true, okay, fine. But you're not doing science. Science means you experimented and you ruled something out by direct experiment. Tell me, where's the experiment that tells us that that's what's happening? There isn't one. That's just people making stuff up, which is fine, but it's not science.
Well, yeah, and we have to make stuff up. We have to hypothesize because that's how we will eventually figure out what is going on. But it is annoying when people act like they're certain they've already figured it out when clearly that's not the case.
Yeah, and we do this selectively. Like, if you were saying, I've got I mixed boron and sulfur and something, and it will make a battery. No one gets like that about propositions like this. They just go and find out, and it either is or isn't. But there's a category of things where the supposed scientists stop doing science, and they will not admit that they're not doing science anymore.
Worship the crank.
Yeah. And hypotheses are fine. I mean, the fact that you can't test a hypothesis does not make it invalid. It can sit there for 2,000 years before someone finally figures out a way to test it. That's not a problem. But don't act like it's proven science. Right. It's like it's not true.
Right. Before we move on to some meta questions, I was fascinated by how the Greeks viewed ratios and harmonics. And I mean, they're right. Things that are in tune, that are harmonious, they sound good to us. And why is that? Is that an evolutionary thing, a structure of the universe thing? Is that God? What's going on? Why do why do these particular things played in concert sound good, and anything that's off of that sounds discordant? What is that? Is
Great
it just
question.
preference, societal preference?
No, it's obviously not just preference. The only thing I could point to at all would be evolution, and the reason it could be an evolutionary thing is that natural phenomena. I don't know what the right category is, but basically nature is full of resonance. Hello, that, and things that sound like if you hear a resonant sound, it's an organized thing somewhere. If you hear noise, it's the wind. As soon as you hear like a resonant kind of sound, it means it's coming from a cave, or it's a vocalization, or it's
something for us to be attuned to. We want to hear that. Yeah,
right. There's a broad preference for paying attention to that stuff versus not, and that stuff, the category of things that have resonance, I don't even know how to sum it up, but I guess I already said what I'm capable of saying. It's just there's a lot of things that are fundamentally interesting to us and useful to us that have resonance.
Yeah, my biases lead me to your answer too, that it's mostly evolutionary. But then I'm struck by a quandary. There's a difference in the way humans perceive things that seems to be too recent to be explained evolutionary, which is like the difference between how people who grew up in Western civilization immediately get Western music with its 4/4, architecture, whereas when we hear something from ancient China, it just sounds bizarre. And I don't know the neocortex is plastic, so maybe it could be. Maybe the same thing applies, but it seems weird to use an evolutionary description to describe something that recent.
Yeah, I agree. There's definitely more than one thing happening. Yeah. And what I'm talking about is just frequencies that go together or don't go together.
Yeah.
So I'm not aware of any that's not really in any cultural music I'm aware of. They all have tones. Like if they pluck a string, they get a resonant tone. They blow into something and they get a resonant tone. We hit things that are not resonant, like, for percussion, and we're marking time, but we all do that. And that's the part that I think would be evolutionary. The distinction between resonant, or which is in the waveforms are periodic. If it's resonant, you get a periodic waveform. So down to the waveform level and the way the frequencies come in the ear, and the way that the cochlea actually has hairs that resonate to different, that whole thing, it's very biological.
Yeah.
It's wired right into the cortex. Yeah. That's the part that would be evolutionary. Preferring different rhythms and meters and beats and stuff, that's cultural. That would be cultural, in my opinion. But there's the level that, the thing that I don't know what to say about is that higher sense of aesthetics, though.
Mm-hmm.
Like, why is a flute beautiful?
Right. Yeah, we're not going to answer that today, folks. I got 3 questions for you that are all the same question, and they're based on that quote of Einstein's. I don't know if we mentioned it already, but you feature it in your talk, which is as follows, quote, "As far as the laws of mathematics relate to reality, they are not certain. And as far as they are certain, they do not relate to reality." I love that. I think that is an essential truth that I harp on this podcast all the time and write about, and I think people forget. So yeah, I have 3 questions that are sort of based on that. Do you want to talk about Zeno's paradox a little bit? It's a funky word problem that I think of as, the paradox is that you talk wrong. You formulated your word problem incorrectly, and I love word problems. Even as a kid, it's a way to drag math out of abstraction and tie it down to reality, where you can make it something that's useful to humans. So tell us all about Zeno's paradox. And
I love Zeno's
playing about it.
Yeah, I love Zeno's paradox for all the same reasons. Again, it's a real self-contained illustration of perspective shift. Yeah. And it's either trivial and dumb because you're just talking about it wrong, or it's the most profound thing ever.
That's right.
And it means the universe is broken, right?
And it changes the way I bet on sports. Profound.
Right. Right. Take your pick. So Zeno was just sitting there one day, and remember, we're back in ancient Greece. There's no zero and there's no infinity. We haven't talked about infinity, but infinity is just as bad as zero. So they actually come in as a pair. So if you're back there in the ancient time and you are not allowing zero, you also cannot allow infinity. So they didn't believe in infinity. Even though curiously they did believe in that Euclidean line with all those points and an endless supply of points, no matter how many, can subdivide. But that's because they believed in ratios, and you can always chop smaller and smaller pieces, right? So they could have maybe noticed a contradiction there, but they didn't. So Zeno is just saying, look, if I want to walk from here to there, at some point I'm going to cross where I'm halfway there. And then a little while later, I'm going to get half of the remaining way there. And no matter where I am, I still have to get halfway there before I can get there. So no matter how close I am to there, and again, in the real world, when you get so close, you're basically there. But if you're doing math, if you're mathematically in a Euclidean way, no matter how close you are, you can still get halfway there before you get there. And so do you see what's happening? We basically just found an infinite number of tasks that we have to do in order to get anywhere. Because it's like step 1, get halfway there. Step 2, oh, whoops. Step 2 is get halfway there again. Step 3, oh, whoops, I have to get halfway there again. And it never stops. So forever and ever and ever, your next task is get halfway there, and you never get to get there. So how can I ever do an infinite number of things? Obviously I can't. And therefore I can never get there. And yet obviously Zeno would get up and brush his teeth, or, well, I don't know if did they brush their teeth? Probably not. But whatever he would do, he would get up and he would get there every day. So it's not like he didn't get that, but philosophically, that was unsolved.
Right. I love the story because it highlights the thing we've been talking about this whole time, which is the very important thing to have in your bag of tricks mentally is the ability to do a paradigm shift, to change your frame of reference, and more importantly, not to get trapped in one, like the one Zeno just made for you, which if you stayed in it would make you insane. I can't leave. What's the point of me even leaving this chair ever? I'll never get anywhere.
Right. And so the solution to that is just to notice that each time you do one of those tasks, it takes you only half as long as the previous one. But even that didn't quite solve it for the Greeks, because they couldn't add up an infinite number of descending quantities like that. Like, we're pretty familiar. If you've taken enough math, it takes like halfway into high school right now to get to where you know that a half plus a fourth plus an eighth plus a 16th plus ... is equal to 1.
Right.
It's not equal to infinity, even though the ... has infinite many numbers. But because they get smaller and smaller fast enough, it equals 1. And really, that's just a tautology, because all we're saying is that if you started with 1 and you chopped it in half, and then you chopped it in half again, if you did if you just did Zeno's paradox, starting with 1 and chopping it up, obviously you're going to end up with 1.
There's your paradigm shift. How about go back and remember what we're talking about in the first place?
Right, exactly.
A trip of X length, not, whatever rabbit hole Zeno fell into.
Yeah, so it's a finite distance, and it's a finite amount of time, because you do each one in half the time. So there's no problem. But they didn't do infinite series,
Yeah, it brings up my second question, which is all the same question. Unless you believe in Platonic abstractions, math doesn't exist anywhere. It's a bunch of ideas and concepts and tools that we invented to try and figure out what's going on. But there's a map versus territory problem. I know you think along these lines, so do I. Don't confuse the way you think about a thing with the thing itself. It's a problem that neoclassical economists are famous for. They create a model of an economy to understand it, and they abstract out of it all these things like transaction costs and imperfect information and the role of the entrepreneur and a bunch of other things. And then they analyze that and discover a bunch of really useful and interesting things. Then they forget what they did in the first place and look at their model and think that's what the economy is supposed to look at. And they go out and look at messy economies with people and their preferences and uncertainty and entrepreneurship and go, what's wrong? There's a market failure here. This isn't living up to my model. I think climate scientists, especially politicized ones, are guilty of that. And I think mathematicians are also, in the way that we've been describing. Like if you're stuck on your model, like the Greeks were with only ratios and no zero and a bunch of other limitations, you're confusing the map you've created for the territory you're trying to understand. And I think that's a trap we're always susceptible to. And I think you're with me on that, right?
Absolutely. This is one of my favorite things to think about. Yeah. This is what my Substack is all about, because in this, you haven't used the word narrative yet, but these are all the ingredients of narrative. Then the narrative is the story you tell from your perspective after you've shifted around. And every time you shift your perspective and you change your labels, you have a different story. It could appear the way it's told to be a completely different story, but it's about all the same stuff.
And being able to shift that perspective at will is literally a superpower. You will look like somebody who understands a whole lot more and fails to fall into certain logical traps than all your friends if you just have that mental flexibility.
Right. And it's also kryptonite.
Right.
It's a superpower that is kryptonite.
As they all are. I mean, that's why that story's so classic, right?
Yeah.
You just mentioned your Substack. Why don't you name it? We'll also put a link in the video description here, and at hamannature.com you'll find my Substack, and we'll also have the show notes, including a link to your bizarrely named Substack. Tell us all about it.
What? What's so bizarre about Twadpockle? It's spelled just like it sounds. And you put the term Twadpockle is actually the worst possible insult. It's defined to be the worst possible insult you could possibly call somebody. And so the proper pronunciation, there's a little puff of air after the T, because it's like you're spitting it. Twadpockle. So you have to say Twadpockle.
I keep waiting for this to catch on the broader culture. I haven't heard it yet, but
no, that's where it was completely ready to go. It's like pre-wired for the the virality. Of course, I'll have to start publishing again. But
on that Substack, which I recommend, by the way, Bernie thinks in very useful and creative ways, and his writing is always worth checking out. On your Substack, do you have a link to a video of this talk, or have you added that yet? The Forbidden Numbers Hate My Brain talk we've been discussing?
I'm pretty sure it's in there. It's not its own thing. It certainly could be.
How Twadpockle of you.
Yeah, I know. I'm complete Twadpockle for having done that. Yeah. You made me think of something, but I forgot what I was going to say.
That's fine. I do have one big meta question while you think about what it was. We touched on it earlier. I still don't understand exactly what it could possibly mean for our understanding of the universe and its nature to have these mathematical tools that we've been talking about that contain elements that we don't understand. I mean, quantum mechanics is like the perfect replica of that, but we've had it with us for all these paradigm shifts. Like, what you tell me you understand what time space is supposed to mean to an Einsteinian. I don't believe you. I don't think you do. But these things are clearly true in some sense, in that when we turn the crank that we discovered, useful and things that we can build iPhones with come out of it. So what does that mean? What is our understanding? What's missing from it? And like, how do you see the weirdness that's inherent here?
Yeah, well, there's a lot to talk about in there.
Oh yeah.
I think I would bring it all down to this. The root of all that is that just because you have a model that works, it doesn't mean that the thing you're looking at is constructed in any way that resembles that model at all.
Perfect.
And
that's right.
As an electrical engineer, some of the things, I have dealt with. One thing that we do is take something like a Fourier transform. Let me try and explain what that is. It's that when you hear something, we've all heard that there are frequencies involved. Fourier analysis is a branch of math where you take a waveform, you take a function, it goes up and down with x's and y's, it goes up and down and does its stuff. You can convey that function by just telling people what is the y for a given x, or you can break it down into like kind of ingredients, which are frequencies. So you can say this, rather than just listing off what it is at each point, I can tell you, well, it's like a 10 hertz wave plus a 30 hertz wave. That's a different way of describing it. It's the same thing. I'm describing the same thing, but I'm looking at it completely differently. I'm looking at it as what the component waves are that make it up. And the reason Fourier analysis is a thing is because, back to what we said about evolution and the frequencies that we evolved, the resonances, the real world is very resonant. Mm-hmm. And so when we're engineering stuff, we often deal with resonant things, and resonant things are made of frequencies like that. So it's a very useful analysis, but not everything is like that. If you have actual noise, it's not made of resonant frequencies. But the math allows you, if you have the data of noise, and say if you've sampled it into a digital system, if you've got 1,000 numbers that represent noise, in other words, 1,000 random numbers, you can run Fourier analysis on 1,000 random numbers, and it will tell you how much of each frequency is in there. There aren't really, in an ontological way, there aren't really any frequencies in there. Just think about the process. If I made 1,000 truly random numbers by rolling a die or whatever, there's no resonance in there. There aren't any waves in there. I just picked 1,000 random numbers. But if I take enough waves, and it turns out I'll need 1,000, because it's about degrees of freedom. If I have 1,000 numbers and I have 1,000 waves, I can always make 1,000 numbers out of 1,000 waves, even if the numbers weren't made by waves. See, that's the thing. When I have a theory that allows me to make anything out of waves, it invites me to think that everything is actually made of waves. But it's not.
Right.
I can make stuff without waves. So there's no waves because I made it.
So climbing down from that bewildering but fascinating expose into whatever Fourier analysis, at the crux of it, you're talking about tools that help you do things in reality, but not necessarily understand reality. And I want to tell a little story that's, I think, the same thing, at least conceptually. We obviously are just intuitively think that when we open our eyes, we see the world. But the hell we do. Our eyes see almost nothing when it comes to the visible spectrum. So what we're given from our senses is sort of a...
Oh, wait. Asterisk. Our eyes see the entire visible spectrum.
Sure.
Because you said visible.
Oh, I'm sorry.
Say visible.
Yeah, no. Strike that. Say it the right way. Our visible spectrum that we see is a tiny, tiny sliver of the entire spectrum.
Yeah.
So what we're doing, and I think math has a lot to do with this, is we have a user interface for the world, and what it does is it works well enough for us to accomplish things. That's different than saying we have something that allows us to understand the world. Or maybe I should pause and, I mean, you love how, what do words mean? What do you mean by understand the world? Is being able to move in it enough? Is that understanding? Or is there something to understanding the quote unquote objective reality? Maybe it's arguable that it's a thing we just can't do. We're certainly nowhere near it now.
Yeah. Actually, a few episodes back on the Twadpockle report, I talked about simulation theory. It was my first audio, my first podcast episode. And what I see there is, because we live in these bodies, Like we interact through the physical world through these bodies,
Yep.
and these bodies are simulators.
Yep.
If you want a baby step to that, our bodies are filters. Like you said, we see a very small range of the electromagnetic spectrum. There's all kinds of, even just past red, all the infrared. I'm not seeing it. It's all over, but I'm not seeing it. Ultraviolet is happening, and I'm not seeing that. And that's just the electromagnetic spectrum. There's all kinds of other stuff. There are little air currents, maybe some air currents go in my ear, and I hear them very, very detailed, sensitive things that are happening in the right frequency range of the air currents. And everything else is just literally right over my head, right past my ear. And, like the dogs hear more frequencies than we do. So there could be something really significant going on in dog frequency world, and is just not even happening to us. Like, it's not that we don't even notice. It's just literally not there for us because we can't pick it up.
I'll put a link in the show notes to a great talk by, maybe it was an interview with neuroscientist David Eagleman. And he makes that case that you're making very strongly. Essentially, the brain is just locked in this dark box, can't see and can't hear. And what it gets fed is these weird electrochemical impulses that come from our very weird nervous system that's attached to these very faulty sensory equipment. And as you say, what's happening is a simulation is being created for us to experience what we can of the outside world.
Right.
So we're always.
I wouldn't say faulty, because don't be so judgmental. I mean, if an apparatus is very, very sensitive to specific things and rejects almost everything else, isn't that a very exquisite, fancy apparatus?
I can hug and love and appreciate my faulty senses while still acknowledging that I see things that aren't there. I hear things that aren't there. They're not perfect in the sense that, like a lot of people, they search for certainty, and so they want to treat the evidence of our senses as if either they're perfect or they're useless. And it's not the case. They're very imperfect and faulty, and they're still extraordinarily useful.
Absolutely. Well, like every microphone has self noise.
Right.
Because there's something within, you can't make a mechanism that doesn't affect itself in some way. So it's always going to trip over itself in some way while it's trying to detect whatever else is going on. At a minimum, it's got weight. Like every car you build has to carry itself. You can't just carry the weight that the cargo you thought about.
Yeah.
You have to add the car to it because it's got to carry itself to carry the cargo. So every mechanism always includes itself.
That sounds like Zeno would assume you could never build a car.
Right.
It's a recursion there that's stymieing. Well, I encourage people to go to say the name of your Substack again so people can search for it.
The Twadpockle Report. TWADPOCKLE report. All one word.
I highly recommend it. And assuming buried in there somewhere is a link to the video of the talk we've been discussing, Forbidden Numbers Ate My Brain. But before I let you go, is there anything about that talk we didn't cover, or some sort of meta truth you want to spit out while we have you?
Oh, we did a pretty good job. The top idea is just that math is not a bunch of smart people sitting around agreeing with each other because there's only one answer. Math is a bunch of smart people sitting around and arguing about all the stuff that doesn't work. And in the process, they are all looking at things from a slightly different way, and it forces us to. Doing math forces us to keep looking at things a different way because the first way didn't make enough sense.
Yeah, absolutely. Well said. And we didn't do the talk justice. This is just a teeny tiny glimpse through a glass darkly, if that's using that phrase correctly. Oh, and you extend the concepts into really useful social areas too. Just talking about frameworks and knowledge and recursion traps, all sorts of interesting things. So please check it out, folks. But this has been great, Bernie. I love the way you think. Every time you contribute something new on your Substack, I'm thrilled to gobble it up. So thank you for all you do, and thank you for this.
Great, Adam. Thanks for having me. Feeling is neutral.
Awesome, dude. All right, we'll catch you next time on Haman Nature.